Beneath the surface of an heat shield during atmospheric entry, the material is not merely getting hot. Part of it is decomposing into gas. Part becomes a porous char layer, while the exposed surface recedes. Those changes are not automatically signs of failure. They are the mechanism that protects the spacecraft. Instead of trying to remain unchanged in an extreme heat flux, the shield sacrifices a calculated amount of material. Energy is consumed by decomposition and surface reactions. Hot products leave the material, and the remaining layers slow the advance of heat toward the supporting structure. The heat begins with the entry flow. A spacecraft returning at very high speed encounters air that cannot move out of the way gently. A strong shock forms ahead of the vehicle. Across that shock, the gas is compressed and heated. At sufficiently severe conditions, molecules can dissociate, and ionization can occur. Calling the entire process friction is therefore incomplete. Viscous effects matter near the surface, but compression layer chemistry, convection, and sometimes radiation all contribute to the energy arriving at the protection system. The balance depends on speed, atmospheric density, vehicle shape, and trajectory. A blunt body intentionally pushes the shock away from much of the surface. That standoff distance helps reduce direct heating compared with attaching the hottest gas layer to a sharp nose. The blunt shape also creates drag, converting the vehicle's kinetic energy into heat in the surrounding flow and slowing the spacecraft. The heat shield covers the windward region that receives the most severe environment. Are an adhesive or attachment system, a structural shell, and a cabin or payload that must remain far cooler. The problem is not preventing the outer surface from becoming hot. The problem is keeping heat from reaching the back face too quickly. As surface temperature rises, energy conducts inward. In an ordinary solid, the temperature gradient simply moves deeper with time. An ablator is formulated chemically before that heat can penetrate unchanged through the full thickness. At a moving depth below the surface, polymeric constituents undergo pyrolysis. They break down under heat, leaving a rich char and releasing gases. Pyrolysis is not the same as a flame burning freely in oxygen. It is a thermal decomposition process governed by local temperature, pressure, composition, and heating rate. The transformation consumes energy that would otherwise continue raising the solid's temperature. The generated gas travels outward through pores in the char. As it moves, it carries energy from deeper regions toward the surface. Gas injection into the boundary layer can also alter heat transfer at the wall, although its effect depends on the specific material and entry condition. The char layer becomes a temporary thermal barrier. Its porous structure generally conducts heat differently from the original dense material. It is not permanent armor. The outer char can oxidize, erode, sublime, or be mechanically removed by the flow. The surface boundary, therefore, moves inward in a process called recession. Recession must be predictable. If the surface disappears too quickly, insufficient material remains for the later part of entry. If the shield is made excessively thick, the spacecraft carries unnecessary mass through launch and the entire mission. Designers use response models to predict temperature, density, gas generation, and surface loss through time. Trajectory is part of the material design. A steep entry can produce a shorter but more intense heating pulse and higher deceleration. A shallower path can spread heating over a longer time. Peak temperature alone does not determine required thickness. Integrated heat load, pressure, shear, and the allowable face temperature also matter. Orion provides a concrete example. Its heat shield uses Avcoat blocks machined into unique shapes and bonded to an underlying structure. During return, Avcoat lates in a controlled manner. But the material recipe is only one part of the system. Block placement, bond quality, gaps, surface steps, and edge details can change local heating. That is why manufacturing and inspection receive so much attention. A void in a bond line can reduce the route for heat to spread or weaken attachment. A gap between blocks can allow hot flow to penetrate or create a local concentration. Engineers use non-destructive evaluation, dimensional checks, and cycle testing to verify that the assembled shield matches the analyzed configuration. The shield must survive environments before entry as well. Launch vibration, acoustic loading, vacuum, cold soak, moisture exposure and handling can affect material or bonds. A perfect ablator that detached before peak heating would provide no protection. Structural attachment and thermal performance are inseparable. Different spacecraft use different protection strategies. Some regions may use reusable insulating tiles, blankets, or temperature ceramic composites. Ablation is chosen where the heat load, mission frequency, and mass trade favor controlled material loss. A reusable surface and an expendable ablator should not be blended into one imaginary mechanism. Even on one vehicle, the heating is not uniform. Stagnation regions, shoulders, seams, and penetrations experience different combinations of heat flux and pressure. Thickness and material can vary by location. Designers do not simply wrap the capsule in an identical slab and hope the hottest point represents everything else. Follow one packet of energy through the system. Heated gas transfers energy to the surface. Some energy leaves through reradiation. Some drives surface reactions and material loss. Some conducts inward and triggers pyrolysis. Generated gas moves outward through char, while the remaining virgin material and structural layers maintain a steep temperature gradient. The position of the pyrolysis front and the receding surface both change with time. At peak heating, the outer layers can be changing rapidly, while the back face remains comparatively cool, because the thermal wave has not crossed the full thickness. After peak heating, stored energy continues moving inward, so maximum line temperature may occur later than maximum surface heat flux. That delayed response is a crucial engineering detail. Surviving the brightest, hottest instant is not enough. The shield must keep every protected layer within limits throughout the complete temperature history, including the period after the external environment has begun to ease. An ablative heat shield therefore succeeds by controlling its own transformation. One fraction of material becomes gas, another becomes char, another is lost from the surface, and another remains intact to protect the structure. Each fraction plays a different role over time. The shield does not defeat entry heat by refusing to change. It changes according to a predicted sequence, making the incoming energy spend itself on chemistry, gas flow, radiation, and controlled material loss before that energy can reach the spacecraft behind it.